In geometry and physics, spinors are elements of a vector space that can be associated with Euclidean space. Like geometric vectors and more general tensors, spinors transform linearly when the Euclidean space is subjected to a slight rotation. When a sequence of such small rotations is composed to form an overall final rotation, however, the resulting spinor transformation depends on which sequence of small rotations was used. Unlike for vectors and tensors, a spinor transforms to its negative where the space is rotated through a complete turn from 0 degrees to 360 degrees, and it is this property that characterizes spinors. It is also possible to associate a substantially similar notion of spinor to Minkowski space, in which case the Lorentz transformations of special relativity play the role of rotations. Spinors were introduced in geometry by Elie Cartan in 1913. In the 1920s, physicists discovered that spinors are essential to describe the intrinsic angular momentum, or spin, of the electron and other subatomic particles. Spinors are characterized by the specific way in which they behave under rotations. They change in different ways depending not just on the overall final rotation, but the details of how that rotation was achieved. There are two topologically distinguishable classes of paths through rotations that result in the same overall rotation, as famously illustrated by the Bell-trick puzzle. These two inequivalent classes yield spinor transformations of opposite sign. The spin group is the group of all rotations keeping track of the class. It doubly covers the rotation group, since each rotation can be obtained in two inequivalent ways as the endpoint of a path. The space of spinors by definition is equipped with a linear representation of the spin group, meaning that elements of the spin group act as linear transformations on the space of spinors, in a way that genuinely depends on the homotopy class. Although spinors can be defined purely as elements of a representation space of the spin group, they are typically defined as elements of a vector space that carries a linear representation of the Clifford algebra. The Clifford algebra is an associative algebra that can be constructed from Euclidean space and its inner product in a basis-independent way. Both the spin group and its Lie algebra are embedded inside the Clifford algebra in a natural way, and in applications, the Clifford algebra is often the easiest to work with. After choosing an orthonormal basis of Euclidean space, a representation of the Clifford algebra is generated by gamma matrices. Matrices that satisfy a set of canonical anti-commutation relations. The spinors are the column vectors on which these matrices act, in 3 Euclidean dimensions. For instance, the Pauli spin matrices are a set of gamma matrices, and the two-component complex column vectors on which these matrices act are spinors. However, the particular matrix representation of the Clifford algebra, and hence what precisely constitutes a column vector, involves the choice of basis and gamma matrices in an essential way. As a representation of the spin group, this realization of spinors as column vectors will either be irreducible if the dimension is odd, or it will decompose into a pair of so-called half-spin, or WEYL representations if the dimension is even. Introduction. What characterizes spinors and distinguishes them from geometric vectors and other tensors is subtle. Consider applying a rotation to the coordinates of a system. No object in the system itself has moved, only the coordinates have, so there will always be a compensating change in those coordinate values when applied to any object of the system. Geometrical vectors, for example, have components that will undergo the same rotation as the coordinates. More broadly, any tensor associated with the system also has coordinate descriptions that adjust to compensate for changes to the coordinate system itself. Spinors do not appear at this level of the description of a physical system, when one is concerned only with the properties of a single isolated rotation of the coordinates. Rather, spinors appear when we imagine that instead of a single rotation, The coordinate system is gradually rotated between some initial and final configuration. For any of the familiar and intuitive quantities associated with the system, the transformation law does not depend on the precise details of how the coordinates arrived at their final configuration. Spinors, on the other hand, are constructed in such a way that makes them sensitive to how the gradual rotation of the coordinates arrived there. They exhibit path dependence. It turns out that, for any final configuration of the coordinates, there are actually two inequivalent gradual rotations of the coordinate system that result in this same configuration. This ambiguity is called the homotopy class of the gradual rotation. The Bell trick puzzle famously demonstrates two different rotations, one through an angle of 2 pi and the other through an angle of 4 pi, having the same final configurations but different classes. Spinors actually exhibit a sign reversal that genuinely depends on this homotopy class. This distinguishes them from vectors and other tensors, none of which can feel the class. Spinors can be exhibited as concrete objects using a choice of Cartesian coordinates in 3 Euclidean dimensions. For instance, spinors can be constructed by making a choice of Pauli spin matrices corresponding to the 3 coordinate axes. These are 2 times 2 matrices with complex entries, and the 2-component complex column vectors on which these matrices act by matrix multiplication are the spinors. This group acts by conjugation on the real vector space spanned by the Pauli matrices themselves, realizing it as a group of rotations among them, but it also acts on the column vectors. More generally, a Clifford algebra can be constructed from any vector space V equipped with a quadratic form, such as Euclidean space with its standard dot products or Minkowski space with its standard Lorentz metric. Given a suitably normalized basis of V, the Clifford algebra is generated by gamma matrices. Matrices that satisfy a set of canonical anti-commutation relations. And the space of spinors is the space of column vectors with components on which those matrices act. Although the Clifford algebra can be defined abstractly in a coordinate-independent way, its particular realization as a specific algebra of matrices depends on which orthogonal axes the gamma matrices represent. So what precisely constitutes a column vector also depends on such arbitrary choices. The orthogonal Lie algebra and the spin group associated to the quadratic form are both contained in the Clifford algebra. So every Clifford algebra representation also defines a representation of the Lie algebra and the spin group, depending on the dimension and metric signature. This realization of spinors as column vectors may be irreducible, or it may decompose into a pair of so-called half-spin or WEYL representations. Overview. There are essentially 2 frameworks for viewing the notion of a spinor. One is representation theoretic. In this point of view, one knows beforehand that there are some representations of the Lie algebra of the orthogonal group that cannot be formed by the usual tensor constructions. These missing representations are then labeled the spin representations, and the constituents spinors. In this view, a spinor must belong to a representation of the double cover of the rotation group SO, or more generally of double cover of the generalized special orthogonal group SO plus on spaces with metric signature. These double covers are Lie groups, called the spin groups spin or spin. All the properties of spinors, and their applications and derived objects, are manifested first in the spin group. Representations of the double covers of these groups yield projective representations of the groups themselves, which do not meet the full definition of a representation. The other point of view is geometrical. One can explicitly construct the spinors, and then examine how they behave under the action of the relevant Lie groups. This latter approach has the advantage of providing a concrete and elementary description of what a spinor is. However, such a description becomes unwieldy when complicated properties of spinors, such as Fier's identities, are needed. Clifford algebras. The language of Clifford algebras provides a complete picture of the spin representations of all the spin groups. and the various relationships between those representations, via the classification of Clifford algebras. It largely removes the need for ad hoc constructions. In detail, let V be a finite-dimensional complex vector space with non-degenerate bilinear form G. The Clifford algebra C is the algebra generated by V along with the anti-commutation relation xy plus yx equals 2 grams. It is an abstract version of the algebra generated by the gamma or Pauli matrices. If V equals Cn, with the standard form G equals xty equals x1y1 plus xny, we denote the Clifford algebra by Cn. Since by the choice of an orthonormal basis every complex vector space with non-degenerate form is isomorphic to this standard example, this notation is abused more generally if dimc equals n. If n equals 2k is even, Cn is isomorphic as an algebra to the algebra mat of 2k times 2k complex matrices. If n equals 2k plus 1 is odd, C2k plus 1 is isomorphic to the algebra mat of 2 copies of the 2k times 2k complex matrices. Therefore, in either case C has a unique irreducible representation, commonly denoted by delta, of dimension 2, n, 2. Since the Lie algebra so is embedded as a Lie subalgebra in C equipped with the Clifford algebra commutator as Lie bracket, the space delta is also a Lie algebra representation of so-called a spin representation. If n is odd, this Lie algebra representation is irreducible. If n is even, it splits further into two irreducible representations, delta equals delta plus delta minus, called the WEYL or half-spin representations. Irreducible representations over the rails in the case when V is a real vector space are much more intricate, and the reader is referred to the Clifford algebra article for more details. Spin groups spinors form a vector space, usually over the complex numbers, equipped with a linear group representation of the spin group that does not factor through a representation of the group of rotations. The spin group is the group of rotations keeping track of the homotopy class. Spinors are needed to encode basic information about the topology of the group of rotations because that group is not simply connected, but the simply connected spin group is its double cover. So for every rotation there are two elements of the spin group that represent it. Geometric vectors and other tensors cannot feel the difference between these two elements, but they produce opposite signs when they affect ever spin or under the representation. Thinking of the elements of the spin group as homotopy classes of one-parameter families of rotations. Each rotation is represented by two distinct homotopy classes of paths to the identity. If a one-parameter family of rotations is visualized as a ribbon in space, with the arc length parameter of that ribbon being the parameter, then these two distinct homotopy classes are visualized in the two states of the Bell-trick puzzle. The space of spinors is an auxiliary vector space that can be constructed explicitly in coordinates, but ultimately only exists up to isomorphism in that there is no natural construction of them that does not rely on arbitrary choices such as coordinate systems. A notion of spinors can be associated, as such an auxiliary mathematical object, with any vector space equipped with a quadratic form such as Euclidean space with its standard dot product, or Minkowski space with its Lorentz metric. In the latter case, the rotations include the Lorentz boosts, but otherwise the theory is substantially similar. Terminology in physics. The most typical type of spinor, the Dirac Spinor, is an element of the fundamental representation of Cp plus Q. The complexification of the Clifford algebra Cp, into which the spin group spin may be embedded, on a 2k or 2k plus 1 dimensional space. A Dirac Spinor may be represented as a vector of 2k complex numbers. In even dimensions, this representation is reducible when taken as a representation of spin and may be decomposed into two. The left-handed and right-handed WEYL spinor representations In addition, sometimes the non-complexified version of CPQ has a smaller real representation, the Majorana Spinor representation. If this happens in an even dimension, the Majorana Spinor representation will sometimes decompose into two Majorana Weyl Spinor representations. Dirac and Weyl spinors are complex representations, while Majorana spinors are real representations. The Dirac, Lorentz, Weyl, and Majorana spinors are interrelated, and their relation can be elucidated on the basis of real geometric algebra. Massive particles, such as electrons, are described as Dirac spinors. The classical neutrino of the Standard Model of particle physics is an example of a Weyl spinor. However, because of observed neutrino oscillation, it is now believed that they are not Weyl spinors, but perhaps instead Majorana spinors. It is not known whether Weyl spinors exist in nature. In 2015, an international team led by Princeton University scientists announced that they had found a quasi-particle that behaves as a Weyl fermion. Spinors in representation theory. One major mathematical application of the construction of spinors is to make possible the explicit construction of linear representations of the Lie algebras of the special orthogonal groups, and consequently spinor representations of the groups themselves. At a more profound level, spinors have been found to be at the heart of approaches to the Atiyah-Singer index theorem, and to provide constructions in particular for discrete series representations of semi-simple groups. The spin representations of the special orthogonal Lie algebras are distinguished from the tensor representations given by Weyl's construction by the weights, whereas the weights of the tensor representations are integer linear combinations of the roots of the Lie algebra. Those of the spin representations are half-integer linear combinations thereof. Explicit details can be found in the spin representation article. Attempts at intuitive understanding the spinor can be described, in simple terms, as vectors of a space, the transformations of which are related in a particular way to rotations in physical space. Stated differently, spinors provide a linear representation of the group of rotations in S-space with any number of dimensions, each spinor having components where or. Several ways of illustrating everyday analogies have been formulated in terms of the platric, tangloids and other examples of orientation entanglement. Nonetheless, the concept is generally considered notoriously difficult to understand, as illustrated by Michael Attiyah's statement that is recounted by Dirac's biographer Graham Farmiloe. No one fully understands spinors. Their algebra is formally understood, but their general significance is mysterious. In some sense they describe the square root of geometry, just as understanding the square root of -1 took centuries. The same might be true of spinors. History. The most general mathematical form of spinors was discovered by Elikatan in 1913. The word spinor was coined by Paul Ehrenfest in his work on quantum physics. Spinors were first applied to mathematical physics by Wolfgang Pauli in 1927, when he introduced his spin matrices. The following year, Paul Dirac discovered the fully relativistic theory of electron spin by showing the connection between spinors and the Lorentz group. By the 1930s, Dirac, Pete Hine and others at the Niels Bohr Institute created toys such as tangloids to teach and model the calculus of spinors. Spinor spaces were represented as left ideals of a matrix algebra in 1930, by G. Uve and by Fritz Sauter. More specifically, instead of representing spinors as complex-valued 2D column vectors as Pauli had done, they represented them as complex-valued 2 times 2 matrices in which only the elements of the left column are non-zero. In this manner the spinor space became a minimal left ideal in Mat. In 1947, Marcel Ries constructed spinor spaces as elements of a minimal left ideal of Clifford algebras. In 1966–1967, David Hestenes replaced Spinor spaces by the even subalgebra C01-3 of the space-time algebra C1-3. As of the 1980s, the theoretical physics group at Birkbeck College around David Bohm and Basil Hiley has been developing algebraic approaches to quantum theory that build on Sauter and Rie's identification of spinors with minimal left ideals.